So it's time to get going. So our second speaker is Aritram from the UF, and he will talk about partitions with bounded largest part and the fixed integral GBG-rank module price. Thank you. Welcome.
Thank you, Dr. Fu, and I would like to thank the organizers for providing me the opportunity to share my research. So today I will be speaking on partitions with bounded largest part and integral GBG-rank modulo primes. And this is joint work with my PhD advisor, Professor Alexander Berkovich. So here is a picture of Professor Berkovich. And okay, so I would like to start with some preliminary background on partitions. So Swati just told about partitions, but then let's see it again. So a partition is a non-increasing finite sequence of non-negative integers in that form, lambda1, lambda2, dot, 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 where lambda i's are called the parts of pi. And the norm of pi is the sum of the parts of pi. And we say that pi is a partition of n if the norm is n. So here is an example. So there are the 7 partitions of 5 listed here. And we may also write a partition in terms of its frequencies. So for the 7 partitions of 5, here are the partitions listed in terms of their frequencies. And P from now on will denote the set of all partitions. So the Young diagram of a partition is a way to represent the partition graphically, where the rows are depicted, where the parts are depicted as rows of cells. So here is a Young diagram. And given the Young diagram of a partition, we can label a cell in the ith row and jth column by the least non-negative integer congruent to j minus I modulo t. So if we consider the example of 10743, we construct the Young diagram, and then we label the cells as 0, 1s, and 2s. So those are the residues modulo 3. And note that we label diagonally 0, and then we go to the next diagonal with 1s, then 2s, and so on. And this diagram will then be the T residue diagram in general, and for this we have the 3 residue diagram here. Okay, so now we can associate a vector to a partition. So we call this R vector, and it's a T-dimensional vector where the component Ri is the number of cells labeled I in the T residue diagram. So if we go back to our previous example, then here R0 will be the number of zeros, which is 8 here. R1 is the number of ones, which if you count, it's again 8, and R2 is also 8. So R vector is the vector 8, 8, 8. And then we have N vector. So it's also a T-dimensional vector where Ni will be Ri minus Ri plus 1. So that's the successive differences of the Ri's. And Nt minus 1 will be Rt minus 1 minus R0. So N vector for our previous example is 0, 0, 0. All right, so now we draw the T residue diagram, and then we can consider our row which is to the top of the first row, and a column which is to the left of the first column as the infinite 0th row and the infinite 0th column. And we can label them in the same fashion we label the T residue diagram, and we call such a diagram to be an extended T residue diagram. So for this partition 10743, this is the extended 3 residue diagram. Okay, so now we introduce 2 partition statistics. So by a statistic, I mean a function from the set of partitions to integers. So in 2008, Berkovich and Frank Garvan introduced a partition statistic called the GBG-rank, which they call the generalized Berkovich-Garvan rank of a partition modulo t for an integer t as the sum j from 0 to t minus 1 rj times omega t to the j, where omega t is the tth root of unity and I is, as usual, the square root of -1. So by this definition, if we look at our previous example, there in the 3 residue diagram, we have R0, R1, R2 as 8, 8, 8 from R vector. And so the GBG rank modulo 3 of the partition will be 0. And in 2006, they introduced, so first they introduced the the special case t equals 2, where they defined it, and then they generalized it later on to the special case t, to the case t. So for t equals 2, they call it the BG rank, and it's defined as R0 minus R1. And they also showed that it is equal to the number of odd index dot parts minus the number of even index dot parts of the partition. And note that BG rank will always be real, whereas GBG rank can also take complex values. So moving forward, I fixed some notations and conventions which are kind of usual in this theory of partitions and Q series. So for non-negative integers lmn, we define the conventional Q Pokamar symbol as a sub l, which we read as a to the base q sub l. So q is fixed as a base, and it's this finite product 1 minus a dot dot 1 minus a q to the l minus 1. And for absolute value of q less than 1, we have this infinite product, which is the limit of the finite product. And this is for convergence purpose of the infinite product, that we take absolute value of q less than 1. And then we define something called the q binomial or Gaussian coefficient, as which we read as m q choose n, to be this ratio of Q Pokamar symbols for n between 0 and m, and it's 0 otherwise. And it's noteworthy that for mn greater than or equal to 0, m plus n q choose n is the generating function for partitions into at most n parts, each of size at most m. Okay. So the motivation of my talk today comes from two identities of Berkovich and his former PhD student Ali Unchu. So they consider the generating function for the number of partitions into parts having largest part at most n and fixed BG rank equal to k, which they call it BNKQ. And they showed in 2016 that for nu in 0 and 1, B sub 2n plus nu KQ is this nice looking generating function, where in the numerator you have an exponent of q, which is 2k square minus k, and in the denominator you have the product of these two q square Pokamar symbols, where q square is the base, with bounds on the number of parts being these two. And they also showed that in the same paper that if you consider the generating function for partitions into now distinct parts, then and also having largest part at most n and BG rank equal to k, then you have this generating function here, where you have a q square Gaussian coefficient, not the usual q. So the weight is in a sense 2 here now. And the only difference that you can observe between these two identities is if you expand this out as ratios of Q Pokamar symbols, you will have an extra q square 2n plus nu here. So in a sense, they are related somehow, and we will see it later on. All right, so our motivation was the fact that we wanted to generalize these two results. So we wanted to see whether we have similar looking generating functions where we have 3s, 4s as the bases, like q cube or q4 or higher powers of q. And so they proved this result theoretically using analytic methods and recurrences. And they showed that this result follows from that using a small combinatorial bijection. But they never resorted to other combinatorial means to prove this. Okay, so now I introduce something called a rim cell. So in a Young diagram of a partition, if some cell shares a vertex or edge with the rim of the Young diagram, so by the rim I mean if you go back, then this is what I call the rim. And so the cells which are here sharing edges or vertices with the rim are called rim cells. And then we introduce something called rim hook. So a connected collection of rim cells will be called rim hook if you cut off the rim hook from the Young diagram and it still remains a partition. And then a partition will be called a T-core if its Young diagram has no rim hooks of length t. So let's see an example. So if you consider the partition 4 plus 3 plus 2 plus 1 of the number 10, and note that the number 10 is a triangular number. So that's why we call this a staircase partition. Then if you cut off all two rim hooks, rim hooks of length 2, then we don't get a partition after that. So that's why all staircase partitions, if you observe, then they are all 2 cores. Okay, so now we introduce something called a region. So first we draw the extended T residue diagram of the partition, and then the set of all cells ij which satisfies this inequality will be called a region. So let's see for the example that we considered. And by the way, I am keeping this example uniform throughout the talk so that it's better to understand what's going on for the same case. So now what we do is all the diagonals which have zeros on them, we put a line on them, we join them by a line, and then the set of cells which lie below the main diagonal, so that we can call this the main diagonal, will be region 0, because if you check for values of I and j, that satisfies this inequality for r equals 0. And then as we move to the right, at the top, all the numberings will increase, so the regions increase by 1, 1, 2, 3, and so on. And if we go below, they are decreased by 1, so it's -1, -2, and so on. So this is the diagram of the extended T residue diagram with regions. And then we can now construct T infinite binary words, W0 till WT minus 1, consisting of 2 letters N and E. So we will see the significance of N and E just now. Using the following rule. So for the ith word Wi, we call the rth letter E if there is an exposed cell labeled I in the region R. So E stands for exposed. Otherwise, the rth letter of Wi is N. So let's that we were looking at. So if we go to region 0 and the cell label 2 is lying at the end of the row, whereas the cell label 0 and 1 are not lying at the end of the row. So 2 is exposed in region 0, however 0 and 1 are not exposed. Similarly, here in region 1, 1 is exposed. And in that way, for all these infinite regions, we can construct this infinite binary words. So in our case, there are 3 infinite binary words because it was for t equals 3. So we construct these infinite binary words here, and everything to the left of these E's are E's because they are all exposed, and everything to the right of these N's are N's because they are all not exposed. And so now I introduce something called Littlewood decomposition of partitions. So we denote the set of all T cores by PT core. And in 1951, D. Littlewood, so this is not Hardy Littlewood's Littlewood, this is a student of Littlewood, and they are not related. So yeah, I usually I gave this talk somewhere before and I got the same question, so I thought of clarifying it now. So they introduced this map phi1, which is from P, the set of all partitions, to PT cores times the product of P's T times. So that's the map from phi1 of P, which is PT core, and this T tuple partitions. So this is the vector partition, and having the property that if you consider the norm of pi, which is any partition, it's the same as the norm of the T core part plus T times the sum of the norms of each of these partitions. And then they call this vector he calls this vector partition as the T quotient of pi, which we denote by PT quotient. And then in 1990, Garwan, Kim, and Stanton in an inventionist paper showed that the norm of PT core can be computed explicitly using this formula, which is depending on the n vector that we learned before. So we will require this formula later on. Okay, so now for I in 0 and t minus 1, we define chi I to be the largest region in the extended T residue diagram where the cell labeled I is exposed. So let's see here. So the cell labeled 0, I mean for chi 0, it's exposed. The largest region in which it is exposed is 4. because everything to the right is not exposed here, the cell labeled 1, the largest region in which it is exposed is 1, and for the cell level 2, the largest region in which it is exposed is 2. So, and then in 2008, Berkovich and Garvan showed that chi can be computed explicitly using this formula, which is Vi plus Ni, where Vi is the number of parts in the ith component of the T quotient, and Ni is the ith component of N vector. And so for our example that we were looking at, using the 3 binary words from that we saw just before, we just saw that chi0 is 4, chi1 is 1, and chi2 is 2, and N vector is 0, 0, 0. So it follows from the lemma that since we have the three partitions in the 3 quotient, the first component of the 3 quotient of pi will have 4 parts, the second component will have 1 part, and the third component has 2 parts. So we can compute explicitly the T quotient part or the partition, the multi-partition, but all for today's talk we will require is what's the number of parts or what's the bound on the number of parts. We don't require how to compute it explicitly. So now I define a conjugate of a partition. So what we do is we flip the Young diagram across the main diagonal, and that's how we get the conjugate. And then once you have the conjugate, if you see that we have the original partition to be equal to the conjugate partition, then we call that partition to be self-conjugate, and SCP will denote the set of all self-conjugate partitions. So what about the generating function of self-conjugate partitions? Okay, so minus q square L will be the generating function for partitions into distinct odd parts, because here the parts are like 1, 3, 5, and so on, having largest part at most 12 minus 1. And it's easy to show that self-conjugate partitions are in bijection with distinct odd part partitions. And so the generating function for self-conjugate partitions having largest part now at most L will be the same, minus q square sub L. Okay, so now the results. So we wanted to generalize the two identities of Berkovich and Unchu. So let's consider the generating function for the number of partitions into parts less than equal to n, having GBG rank mod t equal to k now. So that's an abstract way of writing it. Then for any prime t, so it's important to consider to look at this one or keep in mind this one. For any prime t, any non-negative integer n and any integer k, we have this generating function here where the largest part is now at most tn plus nu. And if you look at this carefully and set t equals 2, we get the first identity of Berkovich and Unchu. So this one. So here we had 2 q pocamers in the denominator, and now we have p q pocamers. Yeah. And so the next one that we wanted to generalize was for distinct part partitions. So what we consider now is, so distinct parts means the parts occur at most once. So now let's consider parts which repeat no more than t minus 1 times, having largest part at most n and GBG rank mod t equals k. So again, we consider t prime, and then we had this generalization here. And it's beautiful. If you look at this, it's almost the same here, except the fact that here the numerator has this extra factor. And that was the same case for t equals 2 result for Berkovich and Unchu. Okay. So that gives a hint that this might be connected to the first theorem. Okay, so now let's sketch a brief proof of theorem 1. So first, consider any partition having largest part at most tn plus nu, for nu being between 0 and t minus 1. And then consider the Littlewood decomposition of pi. So we have the t core and the t quotient, where the t quotient is of this form. Now let t be any prime and GBG rank be k, which is a fixed integer. And then by the definition of GBG rank, which was the sums of the way ri's times omega t to the j, it's, and that equation has solution in terms of ri if and only if ri's are of this form. So R0 is of the form R plus K for any positive integer, non-negative integer R, and Ri is R for the rest of the i's. And so n vector will be of this form then. You just successively subtract them, the Ri's. And then from Garvan, Kim, and Stanton's formula, we get our norm of PT core to be this tk square minus t minus 1k. So this indeed gives a hint to the numerator, the fact that the numerator has a q exponent which is the same that we got. Okay, so now let's consider the generic extended T residue diagram of a partition having largest part Tn plus mu. So we have these regions here, 0, 1, 2, and so on up to n. So for Tn, that means you have n regions having each of them having T cells in blocks. So you have 0 to T minus 1, 0 to T minus 1 up to the nth region. And then the n plus 1th region will have cells from 0 to T minus 1. And that's how they are arranged. So in this row, you have 0 to nu minus 1. And then this can be anything. This is a rim here. And then if in the extended T residue diagram, if we go to the row above this row, then we have nu to T minus 1. And so if you observe in region nu plus 1, so we consider two cases. So for nu greater than 0, any cell labeled I in the region n plus 1 may be exposed for I being between 0 and nu minus 1, because it may either lie on the rim or it may lie anywhere else. So if it lies on the rim, and also if it lies at the end of a row, it's exposed in the region n plus 1. But if it lies anywhere else, it's not exposed. So the largest region that it can be exposed is then n plus 1. So you have this inequality, which gives the inequality for chi I. And for all other cells which are here, they are not at the end of a row. So that means for I being between nu and T minus 1, the largest region where it can be exposed is a region which is to the left of n plus 1, that's n. So these two inequalities then hold. And then from the lemma of Berkovich and Garvan, we see that those are the two inequalities where these are depending on the number of parts of the ith component of T quotient. Okay, so we keep these two inequalities now here. And now let's consider the case nu equals 0. So nu equals 0 mean we end at this region. We don't have anything to the right. So then any cell labeled I for I being between 0 and T minus 1 in the region n plus 1 is not exposed, because they can't lie on the rim, on the end of a row. So the largest region then where it is exposed is n. And then from the lemma of Berkovich and Garvan, we get this inequality. Now we have to combine these two and these three inequalities together to one single relation, and that's that relation. So we have our bound on the number of parts of the ith component of T quotient. Now it's easy to observe that the generating function for partitions into parts at most n is 1 over q sub n. So these bounds will then contribute to these terms in the denominator. Okay, and that's how we get the theorem 1. And for theorem 2, is it okay? So I will just quickly go to some other results. So what we now do is we apply Littlewood decomposition on self-conjugate partitions as well, and then in a similar way for the generating function for the number of self-conjugate partitions, we have this generating function here, and note that we don't have a q square here, we have a q4 base. And for any odd prime t, we have this generating function as here. Okay, so now quickly the last one. So a scope for possible future work. So note that we are doing everything for primes. So it would be interesting to investigate what are the results for composite numbers t. And then in 2023, me and my colleague Avi Mukhopadhyay, we provided a direct combinatorial proof of Berkovich and Unchu's second identity using certain unimodal sequences whose alternating sum equals 0. So in the same spirit, it would be natural to ask whether we have combinatorial proofs for all these results that we showed. But my guess, it won't be easy. Okay, so thank you.
Okay, I
Yes.
think we don't have the time for questions.
Oh, okay.
Yeah.
Yeah, sure.
So, thank you.
Thank you.
So,